In section 3.1, we're going to look at some of the basic concepts of probability. Probability is the study that helps us figure out the likelihood that something will happen. It provides a quantitative description of this likelihood. A probability experiment is an action or a trial through which specific results are obtained. Examples of probabilistic experiments would include things such as tossing a single coin, rolling a single die, drawing one card from a deck of cards, or purchasing a lottery ticket. We say that an outcome is the result of a single trial. So for example, when we toss a coin, we could get the outcome of getting a head. If we roll a die, we could get the outcome of rolling a 3. And if we pick a card from the deck of cards, we could get the outcome, which could be like the 7 of diamonds. The first thing, and this is going to be very important as we move through the topic of probability, is being able to define what the sample space is. The sample space is simply the collection of all possible outcomes of a random experiment. For instance, when we toss a single coin, the outcomes that would be possible would be that of either getting a head or a tail, which we'll just kind of shortly abbreviate with an H and a T. If we roll a single-sided die, the sample space for that experiment would be any of the numbers 1, 2, all the way up through 6. Notice that when we talk about a sample space, properly speaking, it is a set. So we should be using set notation for this, which is braces, and then the individual elements of the set are listed separated by commas. We'll look at one more probabilistic event, that of tossing 2 coins. If we toss 2 coins, the outcome from a particular trial would be what we observe in terms of the faces of the 2 coins. If we label the first coin coin 1 and the second coin coin 2, it's possible that both coins could show a head. That'd be heads, heads. It's possible that maybe the first coin shows a head and the second coin shows a tail. That's head, tail. Or the first coin could show the tail, the second coin could show the head. Or possibly maybe both coins show tails. That would be tail, tail. These would be the 4 outcomes that could result in the tossing of 2 coins. Let's take a look at the next example. We say that an event is one or more outcomes of a probability experiment that are of interest for the experiment. For example, if we go back to that of rolling a die, we know what the sample space is. It's all of the outcomes from 1 through 6. An event, which would be a subset, could be, for example, the event of rolling an odd number. This event would include the outcomes 1, 3, and 5. And then an individual outcome, that of rolling a 3, would be a single element. Here's a couple more examples. Again, we saw that if we toss a coin, if that's our experiment, we could have the event of getting a tail. If we roll a single die, we could have the event of getting a 4. If we toss one coin 2 times, we could look at the event of getting a head and then a tail. Or if we roll a single die, we could look at the event of getting an even number. This brings us to the definition of a simple event. A simple event consists of just a single outcome. In other words, it's just an event that can only happen one way from the sample space. For example, the event of tossing a coin and getting a tail, that would be a simple event because there's just one tail on the coin. However, drawing an ace from a deck of cards would not be a simple event because there are 4 aces in the deck of cards. There's the ace of hearts, ace of diamonds, ace of spades, and ace of clubs. So that event of getting an ace can occur 4 different ways, which means that it would not be simple. The event of getting an even number would not be simple either, because we could get either the 2, the 4, or the 6. That would make the event occur, but in particular we see that event can happen in many ways. And then lastly, if we look at the outcome or the event of getting at least a 2, at least a 2 means 2 or more. That would include 2, 3, 4, 5, up to 6 on the die. So that would not be a simple event either. take a look at example 1. Guessing the gender of 3 children in a family. Let's suppose that a family has 3 children. The first thing we want to do is write out what would be the sample space in terms of the potential genders for this family. So if we kind of start with maybe a tree diagram to schematically draw it, it's possible that the first child could be a boy, or the first child could have been a girl. Corresponding to each outcome, once we know what the first child's birth is, again, you'd have 2 possibilities for the birth of the second child. And then once the second child is born, again, you would have 2 possibilities of births for the... And then we had the 2 possibilities for the births of the last child. This tree diagram, if you start at the very beginning and you correspond to a selected choice, that'll give us one outcome. For example, if we choose all of the top rows, it would be boy, boy, boy. We could also have, let's say, boy, boy, girl, or boy, girl, boy, boy, girl, girl. But if we write them all out, we would see that there's going to be a total of 8 different outcomes from the sample space. If event A is the event of having 2 boys, and it's kind of implied here that what they mean by having 2 boys is exactly 2 boys, that outcome can actually happen 3 different ways. It could be boy, boy, girl, or boy, girl, boy, or it could be girl, boy, boy. All 3 of these outcomes would represent that of getting 2 boys, so that event would not be a simple event because it can happen in more than one way. Let's take a look at example 2. Let's suppose that we randomly select 1 card from a deck of cards. If we let event A be that of selecting the 10 of diamonds, then that event would be a simple event because there's only 1 10 of diamonds in the deck. Okay. So the event of selecting precisely the 10 of diamonds would be a simple event. Notice that we could tweak this example 2 just a little bit. Had I asked the question, would the event of getting a 10 be simple, then the answer would have been no, because there'd be 4 different 10s in the deck. You have the 10 of diamonds, 10 of clubs, 10 of hearts, and 10 of spades. So that event wouldn't be simple, but getting the 10 of diamonds would be, because it can happen just one way. Something that will be very useful to us in terms of being able to help us count the size of a sample space is what's referred to as the fundamental counting principle. The fundamental counting principle says that if you have a sequence of steps, and let's suppose that one event, the first event, can happen in m different ways, and that the second event can happen in n different ways, then the number of ways in which the 2 events can occur in sequence is going to be m times n. And this can be extended if you have like 3 events, 4 events, 5 events, etc. The total number of outcomes is simply the number of ways the first step can occur times the number of ways the second step can occur, up to multiplying by the number of ways that the last step can occur. For instance, if we have, let's say, 4 flavors of ice cream and 3 toppings, and if we're going to choose 1 ice cream and 1 topping, then there would be 12 different combinations that we could make. We would have 4 choices, first for the flavor of ice cream. Once we choose our ice cream, we would then have 3 choices for the second step to choose our topping. So we would get a total of 4 times 3, which would be equal to 12 potential outcomes. If we wanted to look at the number of different possible license plates in the state of South Carolina, the traditional style of license plate contains 3 letters followed by 3 digits. Okay? And it's very important, when we say 3 digits, we're referring to singular digit numbers. And the digits would include the numbers 1 through 9, but also the number 0. Okay? So really it's 0 through 9. And if you think about 0 through 9, that's a total of 10 different values. Okay? So the question is, how many of these traditional South Carolina license plates can be formed? And we can think of the creation of a license plate as just a successive selection of the individual places or the spots on that plate. For example, we know that the license plates can look like letter, 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 digit, digit, digit. To create a license plate, we would first have to choose the first letter, of which there's 26 in the alphabet. We would then have to choose the second letter for our plate. Again, there's 26 letters. The third digit assuming third letter, would have 26 possibilities. And now we have to move on to the next spot in the license plate, which would be a digit. There's 10 digits to choose from, 0 through 9 for the first one, 10 digits for the second one, and then 10 digits for the third one. And then once we've made that last selection, we've completed our license plate. So the total number of possibilities would be 26 times 26 times 26 times 10 times 10 times 10, which gives us a total of 17,576,000 different possible license plates. In example 5, let's suppose that we're going to be creating a security system that uses 4 digits. So we have like a 4-digit punch code, and they say that no digit can be repeated. So if you use a digit in one of the spots, it cannot be used anywhere else in the code. The question is, how many different passcodes are possible? Well, once again, if we kind of schematically draw this out, we're going to do a digit, 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 digit. So we have 4 different digits that we need to choose all together. And let's start to create our passcode. When we start out, because we haven't used any numbers yet, we have all 10 digits available to us. So everything from 0 through 9 is still available. However, whatever number we use for the first digit is not going to be allowed to be repeated when we get to the second digit. Therefore, we now only have 9 possible ones to choose from for the second digit. When we move on to the third digit of our passcode, we're not allowed to use the first number we used. We're not allowed to use the second number we used. So now we're down to 8 possibilities for the third digit. And similarly, when we get to the last digit, we can't use any of the previous 3. So now we're down to 7 possibilities for the last digit. Altogether, the total number of passcodes that could be possible would be 10 times 9 times 8 times 7. And that's going to be 5,040. The next thing we're going to come to, this is very important, this is the classical model or the theoretical model of probability. So it's very important that as we kind of remove throughout the remainder of the section, that you're able to distinguish between E, which is an event, versus P of E, which is going to be the probability of E, that is a numerical measure of the likelihood that E will occur. In the classical or theoretical model of probability, we assume that every outcome in the sample space is equally likely to occur. So this will apply to like situations like picking random cards out of a deck, flipping coins, or rolling dice. We define the probability of an event to be the number of outcomes in the event divided by the total outcomes in the sample space. So it's simply the number of ways event E can occur divided by the total size of the sample space. For example, if we wanted to look at the probability of rolling a 4, the probability of rolling a 4, there's 1 4 on the deck, on the die, out of 6 sides. So it would be a probability of 1 out of 6, which if you want as a decimal would round to 0.167. The probability of rolling an even number, well, there's 3 even numbers on the die. You have the numbers 2, 4, and 6. That's 3 outcomes out of our sample space of 6. Which would give us a probability of 1 divided by 2, which is a half. In comparing the two, again, what these will ultimately tell us is the measurement of likelihood that the event would occur. Since the probability of rolling an even number, which is 0.5, is greater than the probability of rolling a 4, which is 0.167, we would say that rolling an even number is a more likely event, or would be more likely to occur, than that of rolling just a 4. Take a look at example 7. Suppose we have our standard deck of cards. The probability that we draw a numeric diamond. So in the deck, there's 13 diamond cards altogether. So the deck is split up. You have half red, half black. That's 26 and 26. And then each color is further subdivided into 2 suits. The 2 red suits are diamonds and hearts. The 2 black suits are spades and clubs. And there's half of 26 or 13 for each suit. The numerical diamond cards, so the cards that have numbers on them are 2 through 10. And 2 through 10 is 9 values altogether. So there's 9 numerical diamond cards, out of the total size of 52, which is the size of the deck. So I'd have a probability of 0.173. The probability of drawing an ace, well, there's 4 aces in the deck out of 52 cards. So that's going to be 4 divided by 52, which is 0.077. When it comes time to kind of evaluate these numbers and to kind of gauge how likely something is, it's important to remember that the probability of an event is always between 0 and 1. Typically, we prefer to express it as a decimal. Some people will also change it to a percent to kind of give it in terms of percent chance. But this is kind of our measuring stick. It's going to be between 0 and 1. For the discrete or the finite sample spaces we're going to look at in Chapter 3, a probability of 0 means that the event would be impossible. The event certainly would not occur. And probability of 1 would be an event that is absolutely likely to occur. It will absolutely certainly happen. Okay? And then in between you have things like a probability of 0.5, which would be like your coin flips. An event that has a probability of 0.5 would be as likely to occur as what it would be to not occur. And then things with a probability of less than 0.5 would be unlikely events, and things with a probability of more than 0.5 would be likely events. Okay. So to kind of look at these two extreme values, for example, if you asked what is the question of getting a head on a two-headed coin, so if you have like a trick coin and both of the sides were heads, then that's 2 heads out of 2 sides, which would be a probability of 1, which would absolutely be certain to occur. However, the probability of getting a tail on that two-headed coin, well, if there's 2 heads, that means that there's no tails, so that'd be 0 out of 2, which would mean that would be an impossible event. For us, we're also going to define the cutoff for unusual events. For us, an unusual event is any event that has a probability less than 0.05, or in other words, any event that occurs less than 5% of the time. We'll take a look at one more thing to finish this section, and that's going to be the empirical model of probability. This is probability that's based on observations obtained from data. Typically, you would want to use this when events are not equally likely. So if you wanted to ask what's the probability of getting into a car accident in Myrtle Beach, or what is the probability that it rains on a given day, those events are not equally likely. You would want to use some empirical data, which would lead us to the empirical or statistical probability model. In this model, to calculate the probability of an event, you simply take the frequency of the event and you divide it by the total frequency. So it's the number of times the event E occurred divided by the total number of observations. Let's take a look at the next example. Suppose we have the number of people that voted in each of the different age ranges. So between 18 to 20, 5.8 million voters. 21 to 24, we had 9.3. And all the way down to the last category, 65 and over, suppose that there was 28.1 for that. If we wanted to calculate the probability that if we pick somebody out at random, that they were between 35 and 44 years old, we would want to know how many people were in that age range. So if we go to the table, that's 25.4. We would need to divide that by the total number of observations. So we'd have to add these all up. We get 146.2. And then the probability that a 35 to 44-year-old would be selected would be 0.174. To calculate the probability that somebody is not between 45 and 64, what you could do is add all of the people that are not in this category. That would be 5.8 plus 9.3 plus 22.7 plus the 25.4. Skip over this one and then add the 28.1. That would give us 91.3. And then that's going to be out of the 146.2. Another idea, which is going to lead us into the rule of the complement here in a moment, is everybody that's not between 45 and 64, we could simply just take the total and subtract those that are between 45 and 64. And then what's left over would be the 91.3, which would tell us the number of people that are not in that category. So a couple of different approaches here. but the probability of selecting somebody that's not between 45 and 64 would be 0.624. We now come to the complement of an event. The complement of an event is simply the set of outcomes in the sample space that are not included in E. And this is typically denoted E prime. Sometimes you'll also see this with an overline or like a bar over top of it, which is typically how I'll write it. But this is E complement. And the probability of the complement of an event and the original event are related via the following formula. The probability of the complement of an event is equal to 1 minus the probability of the event. So for instance, if we looked at the event of rolling a 1 on a die, that can only happen one way, namely you would get the number 1. The probability of getting a 1 would simply be 1 outcome out of 6, which would be 0.167. If we wanted to form the complement of A, which we'll call A prime here, then that's going to be everything in the sample space except what belongs to A. So you just kind of simply just taking the 1 out, removing it, and then what's left over would be the 2, 3, 4, 5, and 6. These would be the elements in A complement. To find its probability, you could just use a simple definition of, well, there's 5 in here, so that probability would be 5 over 6, which is 0.833. Or alternatively, once we found the probability of A, we could have found the probability of its complement by simply just taking this probability and subtracting it from 1. So 2 different ways you can do this. This is kind of the direct approach, but we'll see, especially in the following sections, that oftentimes using the rule of the complement will make our life and make things much, much easier for certain types of questions.